All right, let's do our sound check. Make sure I can hear myself. And it looks like I can. Do I see camera footage? Or is it a frozen screen? Okay, I can see the camera footage. Okay, we are good to go. Let's put away the headphones. And let's see what we have for today. Mainly it's just two problems I want to cover. So the last time we did regular office hours, we covered some techniques for doing integrals. We mainly focused on u substitution, and today you're going to find out why I felt it was important to learn substitution. There's at least one of the problems. There are two problems in particular that I want to do, and if we have time, maybe I'll introduce a third one. But at least one of the problems requires some use of u substitution in order to solve. So without further ado, let's get started on that. So the first problem I want to do in the second video I did on Riemann sums, the one before the last one, we talked about the concept of moment of inertia, and we calculated it for a cylinder, if I'm not mistaken. If I'm not mistaken, we calculated the moment of inertia for a solid cylinder rotating through an axis that goes through its center as shown here. And we were able to get that the moment of inertia for the cylinder is equal to 1/2 of its total mass divided by its overall radius squared. And in case you don't remember, we started with the base formula for the moment of inertia for a point mass. We said that for every individual point within an object, the moment of inertia for an individual point is equal to the mass of that point times the square of the distance from the axis of rotation for that point. And distance from the axis of rotation, of course, is measured perpendicular to the axis of rotation. So if I'm looking at a point here, for example, its distance from the axis of rotation isn't this, or this, or this. It would have to be just the perpendicular distance, this right here. The shortest possible distance that you can draw between a point and a line. So we're going to basically do the same thing, but this time for a different shape, for a different kind of solid that we couldn't do before because I made that video with the assumption that the people watching it didn't know too much about integration. But yeah, the basic idea is that you define the moment of inertia for an individual point within an object, and then you sum that up. You find a way to calculate the sum of the moment of inertias for all of the individual points. And I guess this would end up being some sort of infinite sum, because you can chop a solid object into an infinite number of points, and that eventually turns into some sort of integral. And the pattern you'll find if you do this over and over again is that you're essentially looking for the integral of some r squared times a dm, and this dm will be converted into something times dr in most cases where we need to calculate moment of inertia. That's just the pattern that emerges. That's not supposed to be something that you know right away to do if it's your first time doing these types of problems. Anyway, so what I would like to do today is find the moment of inertia formula for a solid sphere. For a solid sphere, rotated about an axis that goes through its center. I guess maybe I should have drawn it in a different color. Axis of rotation going through the center of a solid sphere, which is not the same as a hollow sphere. Actually, I don't know if we have enough to do the hollow sphere. I'm going to need to think about it and reflect on it, but I don't want to try it today. Well, actually, let me think. I might have a technique that's completely algebra based for it. You know what? I'll reflect on it, and if I feel like it's doable enough without having to reach for... Because there's a way you can do it pretty easily if you know multivariable calculus, but I'm not assuming that. So I'll play around with it, and maybe next time or maybe just in its own dedicated video, if I find there's a way we can do it with just the amount of math I would expect, an AP student to know. If there's a way to do it with that limited amount of math, then we can show that off. But for now, let's just do the solid sphere. For now, let's just do a solid sphere. There's mass on the inside and the outside. So this is a solid sphere, as opposed to a hollow sphere that only has mass on the surface and is completely empty on the inside. Okay, so I want to divide this thing into a bunch of pieces, the sum of which is the total moment of inertia of the whole solid sphere. So what can I cut it into? There's actually two different ways you could do this. You could cut it up into disks. You could cut it up into basically thin cylinders. So you could cut it up into, I guess I'll draw it over here. You could cut it up into little disks like this, and then, oh, I shouldn't have shaded that so early. Oh well. You can chop it up into these disks. I messed this up really badly already. And then underneath that would be another disk. And then under that would be another disk. And you can probably see from this that if I stack a bunch of these disks and I make them super thin, you can probably see that they kind of take on the form of a sphere eventually. You get a shape that's approximately spherical if you stuff enough disks in here. Or the other thing we can do is pretty much the same thing we did last time with the cylinder. We can actually chop this up into cylindrical shells. So how do I want to draw this? Let me think. I want to make sure that I don't, mess it up too badly. I guess I would want to start with the outermost shell, which is going to be this, and then give it a little bit of, there we go. So that's one cylindrical shell, and then the next one will be a little bit taller, I'm not good at drawing these. Let me start that again. How do I want to do this? Let me think. So I want to do, maybe my tallest shell should be drawn first. And then the next one after that. Can be drawn around it. Yeah, I really need to work on how I draw these. I think this is the fundamental weakness of my calculus lessons so far, is just drawing these sort of stacks of items. Oh my goodness, how do I... Let me think. If I start with a sphere, let me start with my sphere. And then I want to chop it up into, I guess we're going to have a cylinder here. And then let's say another cylinder here. Okay, it's not going to look very neat, but we're basically going to have all of these different nested cylinders that we can cut this thing into. Yeah, this is terrible. Maybe if I drew them in different colors. And here I was worried that the math would be the hard part. Turns out it was the art. Okay, yeah, this is not really the best of drawings, but maybe if we look at it from, maybe if we try to picture what this looks like from above. If I'm looking at this from, from over here and looking down the axis, what you would see from a top-down perspective is something that looks like this. And this middle cylindrical shell would be sticking out the closest to your eye, and then the next one would be a little bit farther away, and then the next one would be a little bit farther away, and so on. I hope that makes sense, because I'm not really drawing it all that well. And if we go the cylindrical shell route, actually, I think I'm going to do both. I'm going to try both methods. But let's start with the cylindrical shell route. So each cylindrical shell is going to be, let's see, where's the center of my sphere? I guess I'm going to draw one more sphere, and I'm just going to draw a single random cylindrical shell within it. Let's say I draw the shell here. Okay, let's say we have that particular shell, and then we can draw our rotation axis. There's the center of the shell. Well, the center of one side of the shell, and we can't see the center on the back side. And there we have an individual cylindrical shell. Okay. So this shell is going to have some sort of radius. We're going to call that the radius of that particular shell. R shell, or I guess we could call it Ri. And for every point within this shell, each point is going to be, well, the same distance away from this axis, right? You're basically looking at a circle where all points within that circle are at equal distances from this axis of rotation. So if you have a collection of points that are all the same distance from the center, then the r squared for each of those points is going to be the same. And so if you add up the m times r squared for every point within that shell, the sum of m r shell squared, since the r squared is going to be constant, is going to be fixed for an individual shell, so this is for one shell, you can pull it out of the sum, and you can say it's equal to r squared on the outside times the sum of the masses of each of the individual points within that shell. Well, what's the sum of those masses? If I add up the mass of each and every individual point in the shell, then we just get the mass of an individual shell. Then we just get r squared times the mass of that whole shell. And I should probably just call it r shell. There we go. So that's for an individual shell. Well, we're trying to find the moment of inertia of a whole entire sphere, so we need to add all the shells. We need I solid sphere is equal to the sum of all of the shells, starting from the central shell and moving our way outwards. We're trying to add all of those individual shells. So from shell to shell, I need to come up with some sort of formula that will allow me to calculate all of my individual shells. That's not good wording, but I think you'll see what I'm trying to illustrate in a minute here. So I want to come up with a formula where for some random shell within this series of shells, I can just define the radius of that shell and its mass, because each shell is going to have a different radius and probably a different mass, because it's most likely going to have a different volume. The innermost shell over here, for example, has a lot of height, but doesn't have a very big radius, so its volume is likely not going to be the same as, say, this outermost shell that I drew. That has a big radius but doesn't have that much height. So we need to come up with some sort of formula that applies to each and every shell that depends on, I want to say we want it to depend on just how far, starting from the center, how far out that shell is. I want that to determine how much mass that shell is going to have. So if I have some shell at this particular distance, how can I figure out the mass? Well, the mass of a shell, not capital M, lowercase m, m shell, is going to be equal to the volume of that shell times the density. You might remember this from the last time we did one of these problems. And the density, assuming this solid sphere has uniform density, that's something I should have mentioned. Solid sphere of uniform density. If the density is uniform, then the density is simply equal to the total mass of the sphere divided by its total volume. And this sphere, I'm going to define its total mass as being capital M, and its total volume, well, its radius, I'm going to define as capital R. So we can just use the volume formula for a sphere there. So volume of a shell multiplied by total mass over total volume, 4/3 pi r cubed. Okay, now let's define the volume of a shell. I guess I want to do that over here. Volume of a shell. What is the volume of an individual shell? Well, we talked about that last time. We said, you know, if you take one of these spherical shells and you cut it open, I can redraw the idea. If we take one of these spherical shells and we cut it open, you know, we can draw a dotted line here and cut along there, slice it open, and slowly begin to unroll it. And we end up getting something that looks like this. And then if you flatten it out even further, it ends up looking almost like a rectangular prism. I guess I should have drawn that a little further away. So this is still a curved surface over here, but close enough to being flat, as long as, you know, the thickness isn't too big. And I won't go over exactly how this plays out. You can just look at the video from what was it, the second Riemann sums video, to see how this over here is just the thickness delta R from here to here. That thickness delta R turns into this. This length of the cut over here turns into this. So that's going to be the height of the cylinder. Turns into that. And then, of course, the circumference of that cylindrical shell is going to turn into this. 2 pi r. Okay, and if I multiply those out, then I get volume of an individual shell. I can just treat it like a rectangular prism, as length times width times height is 2 pi RH times delta R. Okay, this is great, but what is H? When we did it for the solid cylinder, H was just a constant. We called it capital H. But here, H is going to be variable, right? The height of this middle cylindrical shell is not the same as the height of this outermost cylindrical shell. So So we're going to need some sort of relationship. We're going to need to rewrite this height in terms of, well, it's going to vary with distance from the axis. The farther away you are from the axis, the smaller the height is. The closer you are to the axis, the greater the height is. So there's got to be some sort of relationship here. And that relationship is going to be based on, let's see. So we take the radius of the shell into account. And then what I want to do is I want to draw a line right there from the center of the sphere to basically the corner of the shell. And that's just going to be a constant value for all of the shells. It's going to be just capital R. It's going to be the original radius of the full sphere. Okay, and I can now draw a right triangle over here. The height of this right triangle is going to be half the height of the cylindrical shell. So I guess we can call it 1/2 h. I guess we can call it 1/2 of little h. And now I can just do Pythagorean theorem. I can say, where do I want to write this? I guess I'll write it over here. I'm going to say big R squared is equal to 1/2 h squared plus r squared. And if I go ahead and try to solve this for h, then I get big R squared minus little r squared equals 1/4 h squared. If I multiply by 4, then I get h is equal to the square root of, where do I want to write this? I guess I'll write it down here. H is equal to the square root of 4 times big R squared minus little r squared. Or in other words, is equal to 2 square root of big R squared minus little r squared. This feels different from the solution that I had before, so I feel like I may have done something wrong. Either that or I have some sort of alternative solution here. But we will go with this for now. So that takes us to, let's switch colors. That allows us to rewrite V shell as two pi r times h is going to be 2 square root big R squared minus little r squared times delta r. Okay, factoring out the 2 over here and merging it with the 2 over there, that would be 4 pi, and then we've got r times the square root of big R squared minus little r squared delta r. Okay, this we can now substitute into the mass for an individual shell. So we get 4 pi r square root big R squared minus little r squared delta r all times big M over 4/3 pi big R cubed. 4 pi cancels with 4 pi. And then 1 over 1/3 becomes a 3, so this is going to be 3. And I guess I'm going to pull out the big M to the front, and I'm going to pull out the big R cubed. 3 big M over big R cubed, those are all constants, times R square root of R squared minus little r squared, square root of big R squared minus little r squared, delta R. Okay, so that is the mass of an individual shell. We need to take that and basically substitute it in here to get the moment of inertia for an individual shell. So I guess we'll continue that on the next page, because this is starting to look really messy. So let's see, moment of inertia for a solid sphere is the sum moment of inertia for a solid sphere, I'm just going to say sphere, is equal to the sum of the moment of inertia for individual cylindrical shells and the moment of inertia of an individual shell is equal to the mass of that shell times the radius of that shell squared. I just called it R over here because I didn't want to write the word shell every single time. So it's going to be equal to M shell, I guess we'll call it M of shell number I. Okay, fine, I'll just write the word shell, M shell I times radius of that shell squared. And then the mass of the shell is this over here, 3 big M over R cubed. I need to copy it one bit at a time. Three big M over R cubed, big R cubed, times, what did we have? Little r square root big R squared minus little r squared, little r. This is R shell, by the way, so I'll just call it Ri from now on. Big R squared minus little r squared, delta R. And this infinite sum can be rewritten as an integral. This infinite sum just becomes the integral. I'm going to pull out all of these constants. They can be factored out. 3m over big R cubed. Oh, wait, no, I'm not done yet. This was all the mass of the shell. I also need to multiply by the radius of the shell squared, so multiplied by Ri squared. Okay, there we go. Pull out the constants, and now you have a sum of, let's see, Ri squared times Ri is Ri cubed, and then square root of big R squared minus Ri squared, delta R. And this can be rewritten as an integral. This amounts to the integral of r cubed square root of big R squared minus little r squared dr. And this is going to start with our central shell, which is going to be at distance 0, and we're going to keep going until the shell at the outermost edge of our sphere with radius big R. Well, I think I can confidently say we won't have time for a third problem after all, looking at how long this is taking. Hopefully I can still keep this all under an hour, but we'll see. Well, it doesn't have to be under an hour, just around an hour, because that's how much time I actually prepared for. Okay, how on earth are we going to do this now? Well, square root of r squared minus square root of big R squared minus little r squared doesn't look like it's going to be very easy to do without using some sort of substitution. So let's do, what kind of u substitution do I want to make? I'll do u equals big R squared minus little r squared equals, or not equals, gives me du is derivative of a constant is just 0. Derivative of negative r squared is going to be negative 2r dr. And let's see what we can do with that. So I get 3m over big R cubed integral from r equals 0 to r equals big R. Very important to write that now because we're switching variables. And then I get, so if I want a negative 2r dr, I guess I'm going to multiply by negative 2 over negative 2. And I'm going to take one of the r's from r cubed, leaving behind r squared. So negative 2r dr becomes du, and I'm left with 1 over negative 2, negative 1/2. Negative 1/2. What's left there is r squared, and then square root, that's just going to become the square root of u. And yeah, I took my negative 2r dr, so now I should have a du. Okay. I still need to deal with this r squared and rewrite it in terms of u. This is why I spent so much time last week going over back substitution. So what we can do is we can solve for r squared. If I add r squared to both sides and subtract u, then this equation rearranged becomes r squared equals big R squared minus u. So I'm gonna have, I'll pull the negative 1/2 out into the front, so that becomes negative 3m over 2 big R cubed, integral from r equals 0 to r equals big R. And then the little r squared can be replaced with big R squared minus u, all times square root of u, which can be rewritten as u to the 1/2 du. And from here we can distribute u to the 1/2, so that becomes negative 3m over 2 big R cubed times big R squared u to the 1/2 minus u to the 1 times u to the 1/2. 1 plus 1/2 is 3/2, so that's u to the 3/2 du. And from here I can go in two different ways. I can go in two different directions. I can either rewrite my integration bounds in terms of u. So when r equals 0, u equals big R squared minus 0 squared equals big R squared. And then when r is equal to big R, u equals big R squared minus big R squared equals 0. So I could do that, keep it in terms of u. Or I can just integrate this in terms of u and then go back and rewrite it in terms of r after I'm done integrating, which is what we did last time. Either method should lead to the same result. I'm probably just going to do what I did last time, and after integration rewrite everything that's in terms of u, rewrite it back in terms of r. So let's see, integral of big R squared u to the 1/2, big R squared is a constant, u to the 1/2 becomes u to the 3/2 divided by 3/2. So I guess we'll continue this here. We're going to get big R squared u to the 3/2 divided by 3/2 minus, and then this is going to be u to the 3/2 plus 1, that's u to the 5/2 divided by 5/2. 3/2 plus 1 is 5/2. Okay, and this is again evaluated from r equals 0 to r equals big R. Not the funnest looking integral, but we can work with it. It's all algebra from here, so negative 3m over 2 big R cubed times big R squared. How do I want to write this? Oh. I guess I'm going to write it as times 2/3 dividing by 3/2 is the same as multiplying by 2/3, and then u to the 3/2 is big R squared minus little r squared to the 3/2 minus, okay, dividing by 5/2 is the same as multiplying by 2/5, so that's 2/5. And then u to the 5/2, that's big R squared minus little r squared to the 5/2. And that is all evaluated from 0 to big R. My goodness. I mean, I wasn't expecting it to be the funnest problem, but I feel like I did it faster when I practiced it before. Wait, this color is too similar to the previous one. Let me pick something different. Pink. Okay, let's see. So negative 3 big M over 2 big R cubed times, we've got 2/3 big R squared times, I guess I'll use square brackets for this. It's going to be big R squared minus big R squared to the 3/2 minus big R squared minus 0 squared to the 3/2. That's just this evaluated from 0 to big R. Plugged in big R first, minus plug in 0 for the little r. So that's what that's about. We took this and plugged in top bound and bottom bound. I know it can be pretty hard to follow now that we have such a lengthy expression, but that takes care of our first term, and then minus 2/5 of, now I want to evaluate this from 0 to big R. So that's going to be, I guess it's going to be the same thing, except it's going to be to the 5/2. So it's going to be big R squared minus plug in big R, and then that's to the 5/2. And then minus big R squared minus little r squared becomes 0 squared here to the 5/2. Oh boy. Well, the good news is, what color do I want to use here? Let's use this one. The good news is that this is a 0, and this is a 0, so that's some relief. And then we've got big R squared to the 3/2 is left out of this one. Equals, is this part of the page still visible on the screen? Let me double check that real quick. Yes, it is. Okay. We've got 2/3 big R squared times, in this first set of brackets, we've got negative just big R squared to the 3/2. That's the square root of R squared cubed if you rewrite it. That's what raising something to the 3/2 means. It's taking its square root and then cubing it, or cubing it and then taking its square root, either way. And then minus 2/5 of, let's see, what's left in the brackets, that's a 0, and then we've got a negative, and then big R squared to the 5/2, that's the square root of big R squared to the 5th power. My, oh my, we're getting there. We're getting there. So we have negative 3 big M over 2 big R cubed times 2/3. We've got R squared here, and negative, I guess that's just going to be R when you take care of the square root, and then you cube it. So that's going to be times negative R cubed. So times negative R cubed minus 2/5 of negative square root of R squared is just R. So negative big R, and then to the 5th. So negative big R to the 5th. Okay, well, if I distribute the 1 over big R cubed here, then wait a minute. I'm missing something. Oh, I forgot to copy this. There's supposed to be a big R squared over here. Almost forgot it. Big R squared. Okay, there we go. Okay, so if I distribute this R cubed in the denominator, then this is gone, and this r to the fifth reduces to r squared. And if I distribute the 2 in the denominator, then this 2 cancels out with these 2's. So I'm left with negative 3m. Oh, and if I distribute the negative, come to think of it, this negative cancels with that negative and that negative. So that's the negative taken care of. So now I've got 3m times, what's left? I've got a 1/3 and an r squared. 1/3 r squared minus, this reduces to, I should have written them as ones over here, reduces to 1/5 r squared. 1/3 minus 1/5. Let's see, so 1/3 is 5/15 minus 1/5 is equal to 3/15. That's going to be 2/15. So we've got 3m times 2/15 of r squared. So we've got 3m times 2/15 of big R squared. 2/15 and 3, the 3 and the 15 reduce to a 1 and a 5, so that's 2/5. We get 2/5 the mass times the radius of the sphere squared. And there we go. Woo! That took almost an hour on its own. Okay, maybe I won't do it using disks after all. Maybe we'll save that for a later time, or maybe I'll just save it as an exercise for you guys to try. But basically, I'll give you at least the setup. You would calculate the moment of inertia using disks by doing moment of inertia for the whole sphere equals the sum for the moment of inertia of each disk, and the moment of inertia for a disk, well, you already know from the formula for a cylinder, because a disk is really just a cylinder with a really short height. It's just going to be equal to 1/2 the mass of that particular disk times the radius of that disk squared. And of course, each of your disks is going to have a different radius and a different mass, right? Some of the disks on this stack are going to have a bigger radius than others. So that's something you're going to need to take into account. And you're going to have to do something kind of like what I did over here. You're going to have to do a little bit of Pythagorean theorem stuff. But yeah, if you kind of imitate what I did over here, then you should be able to get some other solution that also evaluates to 2/5 the mass of the full sphere over the radius, or times the radius of the full sphere squared. That is what you're supposed to be getting, so you have a way of checking your work. But yeah, I encourage you to try and do this. It should be doable with just algebra and geometry. Well, for setting it up, at least. You don't need multivariable calculus to solve it this way, is what I'm trying to say. Also, there's a bit of a shortcut you can take using the disk method, which is you can just do half of the sphere and multiply by 2. I'm pretty sure that would work, right? Let me think here. Yeah, it should work if you just do it from, the center and then up to one side and then multiply by 2. I don't see why that wouldn't work here. Pretty sure you can take that shortcut, but yeah, that's something you guys can play around with on your own time. As for me, I would actually like to move on to the other problem that I wanted to look at for today, which is the volume of a spherical cap. Let me get this thing. So I bought this thing, I want to say like a week and a half ago, 2 weeks ago, something like that. No, it was 2 weeks ago. It was a little over 2 weeks ago because it was like the night before I did my first projectile motion video for physics. And that was 2 weeks ago, right? I might be misremembering. But anyway, here you've got half of a spherical shell. This is a hollow sphere, as you can see, completely empty on the inside. And if I want to fill this thing with water, to what height would I have to fill it in order for it to be half filled? The answer is not going to be half the height because, well, the bottom side of this thing is not as wide as the top, right? The higher levels of water are going to have, if you think of the water as stacking layers and layers of water on top of each other, the highest layers of the water are much bigger than the lower ones. They account for more volume. So my question is, where is that halfway point really going to be? At what height above the bottom of this sphere will that be? And for that, we need to figure out a formula for the volume of what I learned the other day is known as a spherical cap. That is the problem we're trying to solve. Volume of a spherical cap. Volume of a spherical cap. Okay, I experimented with this a little bit. I want to say it was yesterday, and I think I solved it correctly, but I guess moment of truth is coming. If I mess this up, then I will come back next time with a solution. But let's go ahead and draw out our problem. So we have ourselves, I guess I'm just going to use half of a sphere here. I'm just going to draw a half sphere, a hemisphere. And I want to figure out to what height, if I fill it out to some height h, which is less than its radius r, its radius, I guess I'm going to call its radius big R. That should also be big R, so whether I go, let's use green, whether I go in this direction or in this direction or in any direction really, that distance from the center to the edge of the sphere should always be big R. So yeah, I want to figure out what the volume is at this height. What is the volume at that height? I'm probably not drawing this really well. on earth am I going to figure out this volume? Well, I think we can just cut this up into a bunch of disks and do it that way. We could do it with, you'd have essentially a top disk, and then underneath it is another disk, and then underneath that is another disk. Drawing skills still need work, as you can see. But yeah, eventually the disks get smaller and smaller, and they're supposed to add up to some sort of hemispherical shape. So we could do that, and I think that's the approach I'm going to go with. And so I guess we're going to need to define the volume of an individual disk. Volume of an individual disk, volume of an individual layer is just going to be the radius of that layer. So I'm going to pick out, let's say, this disk over here. Let's say I draw that individually, and it's going to have its own radius, little r, which is going to be less than big R, most likely. And it's going to have some sort of fraction of this total height. I'm going to call that delta H. And I guess that's all we need to calculate its volume. So its volume would be, for a disk is basically just a short cylinder, so it would just be area times height, pi r squared times delta H. And now I see that this r squared and this delta H are not the same variable, so I need to rewrite one in terms of the other, right? Because if this is going to turn into an integral, if I do it right away, I'm just going to get pi r squared dh. My dh does not match my r squared variable, so gotta find a way to rewrite one of them in terms of the other. And I think what I want to use is what do I want to use here? I guess I can, well, okay, so we have up here is going to be the center of the overall sphere. We're going to have some sort of, I'm just looking at a cross section of this. So we have that's big R, but also that should be big R. They don't look the same because I drew this poorly, but they should be the same. And I guess for an individual disk, if I picked, some random disk over here, some random layer within here, then I guess I should always be able to draw some line of length, big R, to that point. I think I actually want to call this big H. I think I want to call this big H, and I'm going to call the height of the current layer, I'm going to call that little h. And to come up with a relationship between the two, I think I want to draw this one more time so that I don't have this pesky thing in the way. So half circle. That's not looking like a good half circle. We have whatever the perfect water level is supposed to be, and then we have a specific layer that we're targeting. That distance has to be big R. That distance is also big R. This distance is going to be little h. And I guess we can also say that this distance from here up to this level, that has to be big R minus little h. I can do some Pythagorean theorem because I do have a right triangle over here. I do have a right triangle right here. So I can say that there's a relationship. I can copy this triangle over. I can say this is big R minus little h. I don't know what this is yet, but this is going to be, well, what's this? This is going to be the radius. This is going to be the radius of the disk in question, which is actually what I'm looking for. So this is actually perfect. And then that's going to be big R, just copying over that triangle. And yeah, Pythagorean theorem, big R squared equals big R minus h squared plus little r squared. Let's see, that's going to be big R squared equals, if I FOIL this, I get big R squared minus 2 big R little h plus little h squared, and then plus little r squared. I can subtract r squared from both sides, and I'm left with 0 equals, I guess I'm going to say h squared minus 2 big R h plus r squared. What do I want to do next? I guess I want to solve for r squared, so add 2rh and subtract h squared, and I get little r squared equals 2 big RH minus little h squared. Did I do all that right? It does look right to me so far. Okay, and with this I can now rewrite r, or actually r squared rather, volume of an individual disk is pi times 2 big R h minus h squared, and then delta h. And I think I have it. I think I now have it. So if I now take the sum the infinite sum, well, I should actually be writing these as from I equals 0 to I equals n, and then taking the limit as n approaches infinity. But, you know, I'm just simplifying the notation a little bit and skipping some steps. Probably should have mentioned that when I was doing the previous problem. But better late than never. So we get pi, hold on. It's the sum of a bunch of disks, And then that can be rewritten as the infinite sum of pi 2rh minus h squared delta h, and then this becomes an integral pi 2rh minus h squared dh. The pi is a constant. I can factor it out of the integral, but more importantly, what are my integration bounds? So the way I've defined h is it's going to start at the bottom. It's going to start at a height of 0, and it's going to go up to a height of big H. Okay, let's see if we can work that out in the space down here. I get the feeling we're probably going to have to continue this on another page, but let's see what happens. So pi integral from 0 to big H of 2r little h minus little h squared dh. Okay, integral of 2rh dh. Well, the 2 and the r are constants. H integrates to 1/2 h squared, so I'm going to have pi times 2r 1/2 h squared minus h squared is going to integrate to h cubed over 3, so 1/3 h cubed, and that's all evaluated from h equals 0 to h equals big H. That's going to be pi times let's see, the 2 and the 1/2 cancel each other out, and so I've got r times, for little h squared, I'm going to plug in big H and 0. So plugging in big H, I get big H squared. Plugging in 0, I get 0 squared. And the difference of the two is going to be my definite integral. Minus 1/3 little h cubed. So for little h cubed, I'm going to plug in big H and 0. So big H will give me big H cubed. And if I plug in 0, I get 0 cubed. Okay, so I'm left with pi times r big H squared minus 1/3 h cubed. I feel like I may have done something wrong here. Let me double check my work. Oh, no, it's right, because I'm just looking at basically the units. I've got units of distance times units of distance squared, so that should be units of volume, right? If this was in meters, for example, it would be meters times meters squared equals cubic meters, and then this is just something cubed, so that's also going to be in cubic meters or whatever length units you choose. So yeah, it's in cubic units. It makes sense. It's a volume of some sort. Okay. False alarm. And yeah, I guess that is it. So now I go back to the original question. To what height? What is this height big H that is required for half of this hemispherical shell to be filled up? Well, I'm going to have to compare that to the total volume. So I'm looking for, so what I have here basically is just a general formula for a hemispherical shell filled to any height h, what volume would it contain? My question is, what color do I want to pick? I guess I haven't used orange in a while. My question is, how high does this h need to be in order for the volume to be equivalent to half the volume of the whole hemisphere? So volume of a hemisphere is 1/2 the volume of a sphere, 1/2 of 4/3 pi r cubed. And I need that volume to be equal to pi times RH minus 1/3 h cubed. Is this even solvable without the need for like computers? I'm not entirely sure. The pi's cancel out on both sides. 1/2 and 4 can reduce to a 2. So now I have 2/3 r cubed equals RH minus 1/3 h cubed. And if I multiply everything by 3, I get 2r cubed equals 3RH minus h cubed. Oh goodness, how do I solve this for h? How am I going to solve this for h? I don't know if it can be done. Is there maybe some sort of factorization I might be missing here that I can do to simplify? Well, let's try this. 2r cubed equals 3r minus h squared all times h. Does that do anything for me? Doesn't look like it. I might be missing something really obvious here, but I don't know what to do from here to untangle the big H from the big R. Okay, well, I guess I'm just gonna go ahead and put this into a calculator and see what I can get for it. So give me a minute here and let me check what Desmos has to say about this. So let's see, what do I want to do here? I guess I'm just going to use x and y in place of my r and h. So I'm looking for 2x cubed equals 3xy minus y cubed minus y cubed. And I'm just getting some sort of graph. Hold on. Brain malfunction. Give me a minute to gather my thoughts. How do I want to put this into Desmos? We are looking for an h that satisfies this equation. So what am I missing here? I think I'm just having a major brain malfunction. Oh well, I think what I'll do is just wrap things up here and I'll post, I guess, in the description or in a pinned comment or something, whatever I get. Because right now I need to go back and look at this with a clear mind because I don't know, maybe I didn't get enough sleep or something, but I'm struggling to figure out what I need to do next here. But yeah, I guess that'll be it for today. I'm not sure what I'll be covering next time. Maybe we'll go back and do this again using the disk method instead of the cylindrical shell method to see that we get the same results. And maybe I will go over like a quick example. Well, I don't know if quick is going to be an accurate description here, but a simple example of using Riemann sums to calculate the total hydrostatic force applied to an object when you dip it in water or whatever liquid to some sort of depth. That's another application of Riemann sums that I'm potentially interested in showing. Not that it's going to be relevant to the physics students because the Physics 1 students are going to be doing everything algebra based anyway, and the Physics C students who do calculus are not doing fluid mechanics. So yeah, I guess it'll be just kind of a just for fun sort of thing. And outside of that, I guess I'm going to need to spend more time thinking about what else I want to cover outside of my weekly physics streams. But that's all stuff that I can do off stream. So anyway, hope this taught you something of utility, and whatever I have next time, hopefully it'll be something just as helpful, if not more. And yeah, I guess that is it. Take care, and I will see you in the next one.